So today we want to talk about Severi-Brauer varieties. A motivating example is the conic associated with a quaternion algebra. Remember that given a quaternion algebra, we can associate to it a conic in P2, the following conic. And we have that the quaternion algebra splits over K if and only if the conic has a K rational point. Actually, later, we'll prove that the two quaternion algebras are isomorphic as K algebra if and only if the conics are isomorphic as algebraic curves. So the conics determine the quaternion algebras uniquely, but then there are advantages that we can use tools from algebraic geometry to study them. We thus think of them as a geometric manifestation, geometric realization of the quaternion algebra. And so naturally, we want to generalize this for any general central simple algebra. We want to find a geometric manifestation for any central simple algebra, and that's going to be the Severi-Brauer varieties. So now let's define Severi-Brauer varieties. Well, to define that, we want to recall the following characterization of central simple algebra. So remember that A is a central simple algebra of degree n over k if and only if there exists some finite extension L over k such that a tensor with L is going to be isomorphic to the matrix algebra MNL. In other words, central simple algebra over K are just K algebras that becomes isomorphic to the matrix algebra. Similarly, a Severi-Brauer variety over K is just a K variety that becomes isomorphic to the projective space. More precisely, a Severi-Brauer variety over K is a algebraic variety over K, so algebraic variety X, such that there exists some finite extension L over K, such that the fiber of X over L is going to be isomorphic to the projective space. And here, it should be PL. Recall that in the case of central simple algebra, if A tensor with L is isomorphic to a matrix algebra, we say that A splits over L. And we borrow the terminology for Severi-Brauer variety also. So if the fiber of X over L is isomorphic to the projective space, then we say that X splits over L. Recall that for a central simple algebra, it's always going to have a finite Galois splitting field. And the same is true for Severi-Brauer variety. It's also going to have a finite Galois splitting field. And one quick remark, because X becomes isomorphic to the projective space after taking fiber product, X itself is originally have to also be smooth and projective. Alright, so that's the definition, but this is not so useful, this definition, because remember originally we defined the Severi-Brauer variety because we want to give a geometric manifestation of central simple algebra. But from this definition, we don't see clearly how, given a central simple algebra, how do we associate to it a Severi-Brauer variety and vice versa, right? So this is not so clear. So now we want to talk about this correspondence. How do we associate to a Severi-Brauer variety a central simple algebra and vice versa? And the key idea here is we'll do that via cohomology. So now let's fix a Gala extension L over K, a finite Gala extension. We will give a correspondence between Severi-Brauer variety of dimension n that splits over L. We will give that a correspondence between that and central simple algebra of degree n that splits over L. And we'll do that by passing through the Gala cohomology with coefficient PGL and L. So to every Severi-Brauer variety, we'll associate a cocycle and recall that we have a bijective correspondence between H1 and central simple algebra of degree n that splits over L. So to that cocycle, we can associate a central simple algebra. And so to review this, we need to review, because this comes from the classification of twisted forms, so we need to review classification of twisted forms. So now let's review quickly the classification of twisted forms of a vector space V with a given tensor phi. So let V be a vector space over K and then phi is some tensor. We say that a pair of K vector space and a tensor psi of the same type as V is a L over K twisted form of V if there is an isomorphism between V tensor L and W tensor L. This isomorphism should preserve the corresponding tensor, so it should send phi to psi. So given a Gala extension L over K, a finite Gala extension, we have a bijection between the twisted L over K twisted forms of V with a Gala cohomology with coefficient in the automorphism of L of V. So this bijection is given as follows. So let's say W, psi is a L over K twisted form of V. In particular, that means we must have some isomorphism F, right, from VL to WL. Right, so we'll associate to it a cocycle, a one cocycle A. One cocycle should be a map from the Gala group to the automorphism group here, and it's going to be defined as follows. So it will send every element sigma in the Gala group to the following automorphism of VL. So we will compose, so F is a map from VL to WL, right? So then F inverse is going to be a map from WL to VL. We're going to compose that with the following map, which I'll call sigma F. So this is defined to be sigma composed with F composed with sigma inverse. So this is going to give us an automorphism from VL to VL. Thus, given an isomorphism between VL and WL, we have associated to it a cocycle, a one cocycle. Now, what if we choose a different isomorphism between VL and WL? Well, then we'll get a different cocycle, but that cocycle is going to be cohomologous to A. So we still get a well-defined class in the cohomology. So this gives us a bijection between L over K twisted form of V and the H1 cohomology group with coefficient automorphism over L of V. Now, how does this have anything to do with central simple algebra? Well, for this, we need to realize that central simple algebra of degree n that splits over L, they're just exactly twisted form, right? L over K twisted forms of the matrix algebra. By definition, A is the central simple algebra of degree n that splits over L if and only if AL is isomorphic to the matrix algebra MNL, right? So then, central simple algebra, so by the results above twisted forms, central simple algebra of degree n that splits over L should be in bijective correspondence with the H1 cohomology group, Gala cohomology, with coefficient in automorphism of the matrix algebra MNK, automorphism over L. So, but what is this automorphism group? Well, this automorphism group is just gonna turn out to be PGL and L because every automorphism of the matrix algebra is gonna be inner. Thus, we got here a bijection between the central simple algebra of degree n splitting over L and the H1 cohomology group with the Gala group L over K with coefficient in PGL and L, right? And the correspondence, the map sends every isomorphism between, so given a central simple algebra A that splits over L, the map sends every isomorphism F between the matrix algebra AL to the following cocycle, the one cocycle. So the one cocycle is going to send every sigma to an automorphism of the matrix algebra as follows. Right, okay. So that's how we associate a central simple algebra to a one cocycle. Now, then the key idea of the correspondence between central simple algebra and Severi-Brauer variety is that for each one cocycle, they also correspond a unique Severi-Brauer variety. So given a Severi-Brauer variety of dimension n that splits over L, right, we can correspond to the cocycle as follows. So let's say X is such a Severi-Brauer variety. Because X splits over L, we have an isomorphism phi between the projective space and XL, right? So we'll associate to it a cocycle, a one cocycle, and the key idea here is that this group PGL and L, we viewed it as the automorphism group of the matrix algebra MNL, right? But we can also view it as the automorphism group of the projective space P to the n-1L. So from given a phi, an isomorphism between the projective space and XL, we can associate to it a cocycle with value in the automorphism group of P to the n-1L by it will send every element sigma of the Gala group to the following automorphism of P to the n-1L. So exactly the same idea as in the case of central simple algebra, but instead of getting an automorphism of the matrix algebra, we now construct an automorphism of the projective space. So this gives us a correspondence between the central simple algebra of degree n that splits over L and the Severi-Brauer variety of dimension n that splits over L. So this is the relative version, and putting all of these relative versions together, we get an absolute version, a bijective correspondence between Severi-Brauer variety of dimension n and central simple algebra of degree n.